Good. Yeah, good morning. The topic of today is model checking with Büchi automata. And let me first repeat what we have seen for finite transition systems versus regular safety properties. So if we had a finite transition system, let's say TS, and we have a regular safety property, so a safety property whose bad prefixes constitute a regular language, let's say P, then what we were doing is basically, okay, we were giving for this an NFA, let's say A, and that's for the bad prefixes of P. So that's the first important step. We are not looking at P itself, but we're looking at the finite words that refute, so that violate P. And then what we were doing is, based on this transition system and this NFA, we constructed a product transition system. And we were checking basically here whether this satisfies the invariant, yeah, so the invariant never F, where F is an accepting state in this bad prefix automaton. So intuitively speaking, we are checking whether the transition system of the model that we are interested in can generate a behavior that violates the safety property. And violating the safety property means it can exhibit a bad prefix. Yeah? And based on this, we were able to say yes, we were able to say no, and if we are able to say no, we could also provide a counterexample. Checking this property amounts to just a simple reachability property. Yeah, so basically this is, how do you do this algorithmically? This basically means reachability analysis. You basically have to check whether in this product transition system you can reach an F state. Yeah. How do you do this in terms of an algorithm? You just do a depth first search. Okay, that's the picture we had so far. And what we're going to do today is we're going to try to generalize this picture towards a larger class of properties. So today my starting point will again be a finite transition system, this finite TS. And on the other hand, I'm going to use an omega regular property. This includes liveness properties, for instance. Yeah? So it's no longer restricted to safety properties, and definitely it's no longer restricted to regular safety properties. So what we're going to do is very similar to this step over there. We're going to build a non-deterministic Büchi automaton. Same philosophy as on the safety properties, not for the property itself, but for those behaviors that refute this property. Again, the principle will be we're going to check whether the transition system can exhibit anything bad. So we're going to construct an NBA A, yeah, for basically the complement of P. Yeah, the complement of P is the property that we want to refute, yeah, the thing that we don't want to have. Now we're going to do the same thing. We're going to take this transition system and this NBA, and actually in the same way as we are going to do there, on the above, we constructed this product with an NFA. Now I'm going to take an NBA. Syntactically, these are the same objects. So the product, as we're going to see, remains the same. And what I'm going to see today is that in this here we're going to check is that we only have finitely often F. I mean, when would this transition system exhibit a bad behavior? If this product can exhibit a behavior which infinitely often reaches an accepting state in this bad automaton A. Yeah? So what we're going to check for, in order to, is finitely often we need to have F. Yeah? Like there we had tracking invariant never F, there we were doing this. And again we're going to see that this gives rise to two possibilities, either yes, we're going to see no, and we're also going to see how we get a counterexample. The second thing what we're going to see today is how to check this. And now what we're going to do is, what we're going to show you is that we don't need a reachability analysis, but we need what we call a nested reachability analysis. And I'm going to tell you the details on how to do what they call a nested depth-first search. Still, this can be done in polynomial time, like in the procedure over there, polynomial in the size of this product, but we need a more involved algorithm. Yeah, and I hope you see that the construction we have seen for those regular safety properties is very similar as over here, but the important point, of course, is that here we use NBAs. Yeah. The bad prefixes is something like the complement. Yeah. And for the rest, what is important is that we now check for this new condition, namely finitely often F, which is the same as saying from some point on, I don't want to see not F anymore. So not F only, basically. Good. Okay, this will be the roadmap of today. So let's start. So this is what we're going to do. As I just explained, an omega regular property, E, it's called here, does the transition system satisfy the property? We're going to construct, as a first step, a non-deterministic Büchi automaton for the complement. So this is the automaton which accepts all behaviors that do not satisfy the property. Then we're going to check whether the transition system, right, cannot generate any bad behavior. The way to do that is by constructing this product. And we're going to check never acceptance condition of A. Never acceptance condition means actually finitely often F. You get an acceptance condition if you have infinitely often F, and that's what we would like to avoid. Okay. The first thing is that this requires an algorithm to check these kind of properties, and that's what we call persistence properties. So what is a persistence property? A persistence property is defined as follows. So I take E as a set of infinite traces. As before, this is an LT property. We call this property persistence if, for some propositional logical formula phi over the set of atomic propositions, it's hold that E is the set of all infinite words over those sets of atomic propositions, such that, yeah, for all but finitely many times you satisfy phi. Good. So from some moment on, phi, or eventually forever phi. That's actually what it means. Good. So it means that you have a trace. Every now and then phi holds, every now and doesn't, but from some point on you only see phi's. Yeah? Good. That's the point here. This is also the case what we need here. You can have an F every now and then in a certain finite prefix, but from some point on you should never see F again. Yeah, because we only want to visit F finitely often. So that corresponds to the notion we need. So here before we had invariance, now we need here a persistence property. That's basically what we're going to see. Good, so this is the picture I just showed you. We're going to build this NBA, etc. And then we're going to check eventually forever not F, which is the same as what we just have seen. Okay, so just let me recall this product. I hope you all remember. This was the synchronous product of a transition system and an NFA. And the idea is that we look at a run or a path fragment in the transition system. We consider the labels of those states, so the set of atomic propositions which holds here, which holds there, and which holds there. And the idea is, intuitively speaking, that these are the input symbols which are fed into this automaton. Okay, so this automaton will, based on these sets of atomic propositions construct a run, and that looks as follows. So here I have a run of this NFA, and I do this based on these input symbols. Okay? And the way to do that in terms of the product construction, and that's the reason why we map S0 to Q1, because what you see, S0 is labeled with A0, with this set of atomic propositions A0, that is fed into this initial state, and then the next state after Q0 is Q1, that is the state that happens after having inputted this symbol A0. And from then on, basically, the transition system and the automaton run synchronously, hand in hand. That's the idea. Good. If this models an automaton that is bad, then it means that if they run synchronously, they together can, if the transition system is able to exhibit a bad behavior, can jointly reach a bad state. Good. So that's exactly what we're going to do now. So the definition of an NFA, this product, was just a synchronous product. So we take the Cartesian product of the states of the transition system and the states of the automaton. And the transition relation was as follows, that if we have a state transition in the transition system from S to S prime by some action alpha, then we look at the pair SQ in the product. When does SQ have an alpha transition? Well, whenever the automaton can follow, basically, follow this transition from S to S prime. What does that mean? It means you feed the symbol of this target state into the automaton. So you consider the current state of the automaton, which is Q. So you look at the transition relation based on the current state Q. You feed this with the input symbol, which is the labeling of S prime, which is LS prime. And you look at what are the possible next states in this automaton. This apparently turns out to be Q prime. But that means in the product, I have a transition from SQ to S prime, Q prime. So the key point here is that the labeling of this target state is used as input to the automaton in state Q. You see a similar phenomenon at the initial states. So the initial states are not the pairs of initial states of the transition system and the automaton, but initial states of the transition system with Q, where you can reach those Qs starting from some initial state by feeding it with as input symbol the labeling of the initial state of the transition system. That corresponds exactly to this cross line over here. You pair this S0 with Q1, not with Q0. Good. That has to do with the fact that one has labels on the states, the other one has labels on the transitions, and you have to match them in some way. That's basically the way that you get this small shift. We're going to label the states with the names of the states and the automaton, and that is represented like here. Good. Now we're doing the same for NBAs. So we're going to adopt exactly the same principle for NBAs. So this is not changing at all. So that's basically the same thing. And now what we want to do is we want to do this, what we call omega regular model checking. We have a finite transition system, an omega regular property E. We want to check whether T satisfies E. And what we do is, as I mentioned, we take the complement of E, which means we take the bad behaviors and construct an NBA for those bad behaviors. And then we're going to reduce it to a persistency checking problem. So this is how it looks like. I have a transition system, I have an automaton. The transition system is over the set of atomic propositions AP, and this is the corresponding set of atomic propositions of the automaton, and that means that the input, the alphabet of this automaton is 2 to the power AP. Good. This, as before, is a non-blocking automaton, which means in every state, for every next input symbol, there is a transition in the automaton. That is what non-blocking means. Yeah? It cannot block in a state because it gets an input symbol for which it doesn't have a transition. Good. So what's the language of accepted by this bad prefix, bad automaton? Not prefix, bad automaton. It's the complement of E. And now we're going to see that the following three statements are equivalent. T satisfies this omega regular property if and only if no infinite trace of T is accepted by this automaton. So this is a difference with the regular safety property. Safety property, we were considering finite traces and finite words. The difference here is we look at infinite traces and an automaton accepting infinite words. Good. This is intuitively not so hard to see. Yeah, I mean, as this automaton accepts everything which is bad, then it means that if the transition system can generate something which is bad, then of course it violates the property. Vice versa, if the transition system violates the property, it needs to be able to produce a trace which is bad, which means it needs to be accepted by this bad automaton. So I think the equivalence between 1 and 2 is relatively easy to see. And now it's also equivalent to 3. So 1 is equivalent to 2 and also equivalent to 3. And that means the product of T and this bad automaton satisfies the property eventually forever not F. And here I would like to spend some words to show you why this is the case. Good. So I want to show that 2 holds if and only if 3 holds. And the way to do that is the following. We're first going to assume this direction, and I'm going to assume the opposite. So basically what I'm going to show is that in fact I'm going to prove first that not 3 implies not 2. Good. So what I'm going to do is assume that my transition system product with A violates this property. Violates eventually forever not F. Now F are the accepting states of NBA A. Good. Let's call this property, just for the sake of simplicity, the property E of A. Good. So now we take a part, pi prime, which is a part in this product. And this violates this property EA. Such a part must exist because otherwise this would not hold. Say pi prime is something of the form S0 Q1, S1 Q2, dot dot dot. As P prime violates this property EA, it means there are infinitely many indices i's such that Qi belongs to F. So if I take this infinite part, I get infinitely many positions where the second component of such a state is an accepting state of this bad automaton. Good. Of course, besides, I know that S0, S1, S2 is a part of TS. That's by construction, otherwise this would not be a part in the product. So this is simply saying if I project only on the first components, I need to get a part in the transition system. Good. Let Q0 be an initial state of the automaton such that this initial state has a transition with the labeling of S0 and moves to Q1. This is the wrong thing. Then we have that Q0, Q1, Q2, etc. is a run in the NBA A for the word LS0, LS1, LS2, etc. This infinite word. And this infinite word, this means this is a trace of some path pi, and this is a trace in the transition system. Since we have infinitely many Qi belongs to F, it means that this run is an accepting run. Hence, the trace of pi belongs to the language of infinite words accepted by A, and that ends this proof. Good. So what you see is that we start with a negation. We assume that the product violates this property, and then we start to basically argue that actually the intersection is not empty, because from this, of course, it follows that the traces of Ts intersected with this A is non-empty. Good. The reasoning the other way around is actually very similar, so I would like to avoid this. So this proof goes in a similar way. Good. So what's the bottom line? The bottom line means we want to check an omega regular property E on a finite transition system. How are we algorithmically going to do this? We're going to use free, which means we're going to construct this product, which is relatively straightforward, which gives us a new transition system. What are we going to do on this new transition system? We're going to check the property eventually for ever not F. And that's an algorithm that I'm going to introduce somewhat later in this lecture. We're going to see this can be done in polynomial time. Good, so here's an example. A very simple transition system, two states, red and green. Suppose I want to check the property infinitely often green. Now, intuitively for us, it's clear that this property is satisfied because you can only cycle around and you get infinitely often green, right? Now, I'm going to apply this strategy. So the first thing what we're going to do is we're going to construct an NBA for the complement. Okay? The complement of infinitely often green is, so the negation, it says from some moment on we see not green. Yeah? We only see not green from some point on. Yeah? Because that means we have a finite prefix. In this finite prefix we can have every now and then green, but from some point on we only see not green. Yeah? Good. What's an NBA for this property, for the complement? From some moment on, not green. My claim is that this non-NBA, for instance, will do the job. We start in this initial state. We have a transition on every input symbol, but as soon as we guess that from some point on we only will see not green, we move from Q0 to QF. And then, of course, we accept only if we have not green, because from some point on we only want to see not green. And then, if we in this accepting state get a green state, we jump out and we never accept again, which means we go to some state Q1 where we stay forever. This is a non-deterministic Buchje automaton. And actually, you cannot model this property. This property, I mean, from some moment on not green, by means of a deterministic Büchi automaton. Remember, deterministic Büchi automaton are strictly less expressive. The key point here is that you need to guess when are we getting to the point where I'm only going to see not green. And this guessing is this non-determinism that I absolutely need here. And you have seen the proof, actually, that you cannot construct a DBA for this property. Good, so now what we have my finite transition system where I have the NBA for the complement. Now we're going to construct the product. Good. This works as follows. My claim is that this is the reachable fragment of the product. Let me try to explain a bit. Where do we start? So what you see here is that we have two initial states. Why do we have two initial states? Well, remember, what's the construction? The construction is you take the initial state of the transition system, which is red. You look at the label of this state. What is the label of this state? Well, it's at least not green, right? So it's not green. What happens if I feed this initial state with the symbol not green? Now, there are two possibilities. Either it stays in the it takes the self loop, which means you stay in Q naught, or you move to QF. And that's the reason why I have two initial states. Yeah? So formally speaking, the initial states are of the form red, Q, red being the initial state of the transition system, Q being an initial state, well, an initial state as follows. It's a kind of state that I reach from the initial state in my automaton by feeding it with the label set of the state red. In my case, this is, for instance, an empty set if we only take green as a set of atomic propositions. What is the set of successor states if I, in Q naught, have empty set? I have those two states, and therefore I have two initial states. Good. As I said, this is exactly the product construction we have seen before. Then, here, for instance, we have a transition. So suppose I have a transition from green to red. Then what happens in this state, green Q0? That means that we're going to look at Q0. We're going to look at the label set of the target state of this transition. The target state is red, so we're going to feed this state as before with the empty set. There are two possible transitions, it's the self loop or moving there, and therefore from this state on we have two outgoing edges to those two states in my product. Good. Same construction as before. So what is important? The important thing is, in my product, when do I reach an accepting state? Okay. Remember, an accepting state means bad. It means that we violate the property of interest. So in this product, the only state of interest is this state, because that's the only state where the second component is the accepting state of the property. I mean, of this NBA. Good. Now, it's, I hope, intuitively obvious to see that in this transition system we can reach an accepting state, but we cannot reach it infinitely often. So this transition system satisfies the property eventually, which means from some point on, we have forever not F. Yeah. Suppose we start here, we're accepting. That's maybe bad, but it's only once. That doesn't hurt. Yeah, finitely often here, that doesn't hurt. So once is okay. Then we move there, and then we stay there ad infinitum, and we will never see an accepting state anymore. Therefore, we satisfy eventually forever not F. The other possibility of an infinite behavior is something like this. Infinitely often there, or finitely often there, and then jumping there, but that's all fine, because at most I will visit an accepting state once. That's only finitely often. That's all fine. Good. Second example. A very simple transition system again. We start in this initial state, then we can try to send a message. The message can get lost, then I go here and then I send the message again. Or the message will be delivered, and if I have the message delivered, I go back to my initial state start. Suppose I want to check the omega regular property. Each sent message, or repeatedly sent, if I have to send it more often, every message that I sent will eventually be delivered. Now, is this a property that holds? No. Yeah, because I can stay in this loop ad infinitum. Yeah? In principle, I can lose a message infinitely often. Good, that's our intuition. How does this work? By means of the scheme that I just explained on the blackboard. So it's clear it violates this property. First, I take the property at hand, I'm going to complement it and build an NBA for the complement. So what's the complement of this property? It says, well, I have some try of a message, but that will never be delivered. No, the property says every message that I send will eventually be delivered. The complement says, well, there is a message that I will never deliver. So what's the NBA for this negation, for this complement? This works as follows. So again, I have three states. Again, it's non-deterministic. So here I have basically I try, it's not delivered, and it will never be delivered. Yeah, that's the idea. Good. So as soon as I am in this state and the message will be delivered, I move out and I will never accept again. Good. Same principle as before. I have a finite transition system. I have an NBA for the bad behaviors. Let's construct a product. This is the product. I'm not going to explain this in much further detail. If you just follow the construction we have seen before, then you will just get this automaton. So what do you see here? What is important is, can we reach an accepting state? Okay? And don't finitely often we want to reach it. If we can reach it infinitely often, this is bad. Yeah? So there are some states which have QF as component, this one and that one, and indeed it's possible to move from start to this state and we stay here ad infinitum. So there is a possibility, which we already knew because we already know that the property is violated, but here we see systematically that indeed we have a possibility of looping here forever, and looping here forever means actually that we violate the property. So this is the labeling of the transition system. The pink states are the important ones because those are the ones where the NBA is accepting. So those indicate the states that are bad. Now we have to check eventually forever not F. This is violated because you can go here and cycle around there. And that's an example or a counterexample for satisfying eventually forever not F. Conclusion, thanks to the theorem we had, if we know this, the original transition system does not satisfy the original property. Good. What I just did already on the blackboard is summarized again here. For regular safety properties, we were checking whether a finite transition system satisfies a regular safety property. For safety properties, it suffices to look at finite bad prefixes, so we look at finite traces and bad prefixes of this property and check whether the intersection is empty. For regular properties, we were checking infinite traces and infinite words, so that's why we used automata like Buggy automata and accepting infinite words. Good, so that's an NFA, that's a BFA, NFA and an NBA, sorry. Here we were checking, yeah, you should never reach an accepting state because a finite automaton is accepting once you reach an accepting state once. Here we are checking eventually forever not F. That means from some point on, we should never visit the accept state anymore. Yeah? And in both cases, F is the set of final or accepting states of this automaton. So I hope you see here that the two schemes are very similar. And I hope you understand why we need automata on infinite words and why we are going to check now this property eventually forever not F. Good. The first was called invariant checking. Invariant checking can be done by a simple depth-first search. The second one is what we call persistent checking. Why persistent checking? This property is a persistence property, right? From some point on, something must hold, namely not F. Good. So that raises the next question. How are we going to check this? How are we going to check whether the product satisfies this property? Good. I'm going to present you two algorithms. One is basically more for intuition. The second one is the one that is actually used in practical model checkers. Good. So the following observation is helpful. my transition system violates eventually forever F. Again, from some point on, I only want to see A's, not FA. What does that mean? It means that if it refutes this property, it means that there must be a path in this transition system, S0, S1, etc., such that, yeah, I have infinitely many positions along this path that violate A. Yeah? This negation comes from this negation. Yeah? Good. But that means there exists a reachable state S such that S violates A. Yeah. Why is this the case? Well, we need a path that has infinitely many positions along this path refuting A. Now the key point is the transition system itself is finite. Yeah? So there are not infinitely many SIs in the transition system. That means there must be some state that you visit infinitely often. So there must exist a reachable state S such that that refutes A and lies on a cycle. Yeah, so the picture is basically as follows. This is my transition system. Yeah. I have maybe several initial states, maybe one here, maybe one there, that's okay. Now there is some state S that is reachable. Maybe from this initial state. And this S lies on a cycle, and that means there is some cycle here that leads you to S, and S refutes A. That's the situation. Good. So now what we need to check whether our transition system has a reachable state that lies on a cycle. How are we going to do this? Well, one way is to look at strongly connected components. I hope you all remember what is a strongly connected component. It's a subgraph such that every node in the subgraph can reach every other node in that subgraph. Yeah? You have mutual reachability within this subgraph. Non-trivial means this subgraph has at least one edge. Yeah? Good. I get to this in a minute. So what is important here? I need to find a strongly connected component that has at least one state that refutes A. Yeah? So basically what I'm saying, I need some kind of strongly connected component. Maybe this looks like follows. So this is maybe the strongly connected component. And this strongly connected component contains at least one state refuting A. Good. So a maximal set of states that I didn't mention, but I hope that's clear. You try to make this set as large as possible that are reachable from each other. And it's called non-trivial if it has at least one edge. That's what I just said. So that means either it's one state with a self-loop or it contains two states, yeah? Or more. So just a state without any outgoing error is not a non-trivial SCC. It's called a trivial SCC. Question?
A question about strongly connected components. If I have three states and three interacted edges.
You have three states, okay.
Would this also be a connected component?
I have three states and then?
Just one circle of...
One cycle, like this. Yeah, this is a strongly connected component. And it's even a non-trivial strongly connected component. Yeah. Good. So this gives us one hint to check this persistence property, namely, take your transition system. Which transition system? Well, this product, right? Because that's what we are considering. Take this product, consider it as a graph, a directed graph. Calculate the strongly connected components, which is a standard procedure you have been taught in the course on data structures and algorithms. And you analyze them. Why do we analyze them? Well, we need to have one that has at least satisfies not A, right? I mean, refutes A. Good. So let's do this for this example. This was the transition system. Remember the property, every sent message, either repeated or not, will eventually be delivered. We considered the negation. So the negation said, okay, I have a message that I tried, but it was never delivered. This was the NBA. We constructed the product. And the previous slide suggests, why don't we just look at the strongly connected components in this product? So let's have a look at this product. Here is the product. Consider the strongly connected components in this product. These are these three. Now you may argue, okay, this is maybe a strongly connected component as well because those two states are mutually reachable, but that's not maximal, right? Remember, a strongly connected component is the maximal set of states which is mutually reachable. So my claim is those three sets are the strongly connected components. Then all these three strongly connected components are reachable. That's important, right? Because we wanted to have this thing reachable. Yeah. So if there are strongly connected components that are not reachable, they're not of any interest here. And then I know that C2 is non-trivial. Actually, they're all three non-trivial. And in particular, it contains at least one state. In this example, the whole SEC contains two states, and they are both accepting, but it suffices for the argument that it has at least one state that is satisfying that it violates not F, right? Look at the double negation, right? We're interested in not F and negation, so we're interested in F. Good. And therefore, we conclude that this transition system, this product, refutes this property. And now we know, thanks to the theorem we have seen before, that this original transition system does not satisfy this property. Yeah? Good. Okay, what is a counterexample? Anyone has a clue? What is now, as a user, I could give back a counterexample. How would that counterexample look like? Now, you look at how to reach this strongly connected component. For the sake of argument, let's take the shortest path from the initial state to this strongly connected component, so let's move there directly. So I move in my transition system from the state start to try to lost, and then I look in this cycle. Yeah? So the counterexample is start, try, lost, try, lost, try, lost, try, lost. And I represent this by moving from start to the loop try, lost. So the counterexample is this form. Is start dot try lost omega. Well, I don't need the omega. I only have to say this is the cycle that I reach, and then everybody knows I can take this cycle infinitely often. Yeah. This is exactly the counterexample you had already in mind when I was explaining this example. The first thing I said, basically, well, look, this doesn't satisfy the property because of this loop. Well, that's exactly the counterexample, because you first go there and then you go to this loop once. Yeah. Good. Okay, so that's what we just have seen. We can check this property, or we can check whether T violates this property if and only if there exists a non-trivial reachable strongly connected component that contains at least one state violating A. Good. So one method is just calculate the strongly connected components, analyze them. Sorry, there was a question. Yeah.
What if the strongly connected component is non-trivial? What if it's trivial? Is it possible that this stays like a set loop?
No. So the question is, what happens if it has a trivial strongly connected component? So what is a trivial strongly connected component? A trivial strongly connected component is something like this form. This is my transition. I go here. Transition system initial state, and I reach a state here that has no outgoing arrow. This violates A, that's all fine. This as itself is a strongly connected component because the state is reachable from itself, right? But it is not trivial. I mean, it's not non-trivial, it's trivial. This is a trivial SEC. Yeah? And you see, I hope you see this doesn't work because I have to reach this state infinitely often. And here I can only reach it once and then stay there, but that doesn't count. I need really to take a cycle. Question?
And if the state has a set loop?
That's okay.
Okay, so trivial just means, what does trivial mean?
Maybe I was too quick, so go back to this slide. Trivial means either you have one state with a self loop, or you have more than one state. So the only case I rule out are these sinks. Yeah? And I hope you see for good reasons. Good. Now, this is conceptually easy to understand, I hope, because you can compute the strongly connected components. But what you typically need to do is you need to have the entire transition system, which means this product, at your disposal. You consider it as a directed graph. Run your favorite algorithm to generate the strongly connected components, and you're done. The point is, however, this is not adequate for an on-the-fly analysis. Many model checkers don't want to generate this whole transition system at once. But what you like to do is basically you gradually take TS, you gradually take the automaton, and you build this whole thing on the fly. Why is this useful? Well, as soon as I even have generated only a partial, so only a fragment of this thing, and I found this reachable cycle which is bad, I'm done, right? Maybe I don't need the whole thing. Now, from a conceptual, from a complexity point of view, this is, of course, my colleague in algorithms and complexity will say, well, I don't care. Yeah, because from a complexity point of view, it doesn't matter. From a practical model checking point of view, it matters a lot. And that's the reason why, actually, I do not know any model checker that uses this SCC procedure. They use what they call a nested depth-first search, and maybe more advanced versions of it. So that's the next algorithm I'm going to explain you. We're going to see a depth-first search, and this depth-first search is what they call a nested depth-first search. Why is it called a nested depth-first search? Well, look at this picture over there. What do we need to do? First, we start in some initial state. The first thing that we have to do is we have to see whether I can reach the state violating A. Yeah, so I have to do this. Yeah, that's my first depth-first search. So suppose that in my orange depth-first search I have found a state that is reachable violating A. Now I have to check the second condition. I have to check whether this state lies on a cycle. So I'm going to initiate a next depth-first search. Let's do this in purple. And that means I'm going to start a next depth-first search in this state to check, does this state S lie on a cycle? Okay? So I'm nesting an orange depth-first search with this purple depth-first search. And this is why the term is called a nested depth-first search. Good. If you do this naively, then in the worst case, the orange one has to explore the whole state space. For every state that you explore during the orange depth-first search, you have to also do the purple depth-first search. Now, I hope you all remember at the top of your head that the depth-first search is linear in the number of states and edges in the graph. But if for every orange state I have to do another depth-first search, I get the number of states times the complexity of doing a depth-first search for every state, right? So it's n times n. This is expensive. So that's why I need a couple of tricks to make this more efficient. Good. So let's first do the principle and then do the tricks. So we have a finite directed graph. How on earth do I get this finite directed graph? Well, I take this object, I consider this as my graph. So here is my graph. And I have this node S, or vertex, in my graph. Then the two statements are equivalent. G is cyclic, so, which means G has a cycle. If and only if the depth-first search starting somewhere in G finds some backwards edge. Backwards means you are in a state and you find an edge back to the state where you initiated before some depth-first search. Good. So a cycle check in a digraph can be done by doing a depth-first search. You start in some arbitrary pace. You check whether there is a backwards edge. So you check whether at some point you reach the state somewhat later in your depth-first search, which can move back to one of the states that you have seen before. If that's the case, you close the cycle, you have found the cycle. Good. Complexity, linear in the size of the graph. The size of the graph is the sum of the number of vertices plus the number of nodes. Good. So, applied here, suppose I have a node in G, then S belongs to a cycle, so it starts in S and it ends in S, right? And actually this is, again, non-trivial, so there needs to be at least one edge from S to S. Just being in the sink S doesn't count, it's not a cycle. Is equivalent to saying, if I start my depth-first search at S, so at the beginning here, it at some point will find a backwards edge. Yeah. So the cycle check for a fixed node, if I fix a node in my transition system, like for instance this S over here, then the question, does S belong to a cycle? What are we going to do? We're going to do the purple depth first search. We're going to perform this depth first search. You start in the state you just have entered, and you check whether you will find, during this depth first search, a backwards edge that goes back to S. Then you're done. Good. So this is the problem we are confronted with. Does my finite transition system satisfy eventually forever A? A in our case is not F, but that's just to make life a bit simpler. So one way to do this is initially you don't mark any states, so all states are unmarked, and then you repeat the following procedure. You choose an unmarked reachable state S that violates A. So you found one of those S's. Now you're going to check whether this thing lies on a cycle. How are we going to do this? We're going to mark it. Let's color it purple, so that we start this purple DFS. We're going to check whether it's on a cycle. If it's on a cycle, then the problem is no. Yeah, because if it's on the cycle, we refute the whole thing, so then we get no. And you do this until you have checked all the reachable states that violate A. Yeah, I hope that's clear. It could be the case that here I have another state that I can reach from there which violates A. I also have to check whether this is on a cycle. As soon as I have found one which is on a cycle, I'm done. As long as this is not the case, I have to consider them all. So I repeat this until I have checked all reachable states in my transition system or in the graph. And that's basically the case. And if I did this and I did not find anyone on the cycle, then the answer is yes. Good. So here I have the outermost depth first search. In my picture there it was orange. This is what is called here the first depth first search. You have to check first reachable. You have to search for reachable states violating A. And then there is a second depth first search, which is here, which is in this case the yellow one, where I do the cycle check. Good. And this is what is called the term nested depth first search, as I already explained. Good. So if you do this naively, then the time complexity is actually the following. First, you have to find all the states violating A. In worst case, every state could violate A. And that means for every state, I have to check whether it's on a cycle, which is another depth first search. And that means there I have to do this complexity. Good. So that's the cost of the cycle check. Good. This is what I would like to avoid. Yeah. Again, an algorithmatician would maybe say, okay, I'm happy it's polynomial, done. We would like to do it a little bit more efficient. And so this works as follows. So we're going to look at, well, I call this a tricky variant. This tricky variant was defined originally in a paper in 1996. 1996, there was a famous paper by Doron Pellet, Israel, Moshe Vardi, Israel, Pierre Volpaire, Belgium, and I have the feeling I missed somebody. Yes, Yanakakis. Yeah. Good. For this paper, they got several, I think, prizes, and this is the tricky variant. Good, let's see. So the idea is the following. The important things I pointed out with yellow. So there are a few important points. So remember, I want to check T. T is this product, right? Ts times A in our setting, satisfies eventually forever A. The first insight is don't do those, let's say, first check in the orange depth first search, all the states violating A, and then for everyone, do this purple depth first search. Do this in a more clever way by letting the two nested depth first search run some way in an interleaved manner. You do a bit of the orange one, you do a bit of the purple one. You do a bit of the purple one, then you do a bit of the orange one, and so forth. Good. So that's the first you visit all the reachable states. Then you do a cycle check for the states violating A in order to check whether S belongs to a cycle. You are going to look, we know, looking for a cycle means try to find a backwards edge. And the important point is, and that's the second thing, we are going to ignore all the states that have been visited before in previous calls of cycle checks. Okay, maybe this is not completely clear in the beginning, so let me try to visualize this. So here is the entire transition system, T. Good. We do the outermost depth first search, which is orange. So let's suppose that at some point we have found a reachable state here, which violates A. Good. There we initiate, does it lie on a cycle or not? A purple depth first search. Let's suppose that here we check this part of the state space because that's reachable from this state, and our conclusion is, bad luck, no cycle. Good, fine, can happen. Now we go to the next state. So maybe from here there is another state which is violating not A. Yeah? Good, okay, again we have found a state which is a potential candidate to show that the property is violated. So we start a cycle check. The trick will be, we don't have to consider this fragment anymore. We're going to see an argument, if we do it in the right way, that we can avoid starting the purple depth first search here to avoid this part of the state space because we have already searched it before. Yeah? So I hope you understand, you don't get this worst case behavior that for every reachable non-A state you have to do the whole state space. Yeah? That's the main trick. So this, basically, you don't have to consider this anymore if you find the second one. And now the argument repeats. So maybe now you have searched this part and you found no cycle. Then again you backtrack in the orange depth first search and you say, well, maybe there is something here, also not A. Potential candidate. Now I don't have to search this one. I don't have to search that fragment of the state space anymore. I can just ignore this. Yeah? And that's the key point. Is this clear? Yeah? Good. And that means we need to keep track of which purple areas we already considered. That's V. Yeah? So this set over here, this belongs to V, and this at some point belongs to V. So after having found this one, after having found that one, after having found that both are not on a cycle, V contains this set plus this set. Yeah. Good. Okay, but be careful, it can go wrong. So we have to be a bit precise. So let's look at this example. So we try to do the procedure, the kind of paradigm we just have seen. So this is my state space, only 4 states. S1, the 2 blue states, they violate A. So they are, for us, the interesting candidates. Yeah? It's obvious this guy doesn't lie on a cycle, that one lies on a cycle. And we know that the other 2 states are not refuting A, so they satisfy A. So I hope it's easy to see that this transition system refutes eventually forever A because of this cycle, and the blue state does not violate A. Good. Intuitively this is clear. Now let's run this procedure. I started a depth first search. This is the orange depth first search. We're in the outermost depth first search. So I'm first looking for the reachable non-A states. S0 itself is not a non-A state, so let's continue. S0 satisfies A, so that's a good guy. Now I find S1. S1 is bad. So I'm going to check, does S1 lie on a cycle? So I initiate the innermost depth first search, the purple one. The purple one says, does a cycle check. It checks. It does a depth first search starting from here. From that one, it does a depth first search starting there. Now I have traversed the whole reachable state space starting from S1. And I conclude, S1 doesn't lie on a cycle. For the rest, I make this area purple. So I never have to visit S1, S2, S3 again in a cycle check. And you see already this is wrong. Yeah, because now you will not find this cycle anymore. Yeah? So this goes wrong, and to see this is the following. So I've done my cycle check for S1. Conclusion, S1 doesn't lie on a cycle. So that means continue our orange, the outermost depth first search. I'm going to look for other reachable non-A states. So I go back. I do a DFS of S3. Why? Well, that's where we stopped, right? That was the bad guy. We initiated the cycle check. Conclusion, no cycle check. Now we continue with the orange one. That means we now continue with S3. And now we're going to, this is a good guy, so we don't have to check anything. Now we're going to get S2. Again, part of the orange depth first search. This is a bad guy. I have to start my purple depth first search. My purple depth first search says, I have already considered all the reachable states starting from S2. And our paradigm was, you'd never have to touch those things again. So the conclusion is, it's not on a cycle, which is the wrong conclusion, of course. So now we do the cycle check, and the paradigm never touch a state that I have already seen in the purple depth first search again. This goes wrong. So this gives a wrong answer. So this order in which we do the orange, the outermost depth first search, and the purple depth first search, the innermost, is not the right order. We have to change this a bit. That's why I call this a bit tricky. Yeah. So this is again these two things. So we're going to check in this cycle whether S belongs to a cycle by searching for a backwards edge. We're going to ignore states that have been visited before in this purple cycle check. And we do this by keeping track of this. But we're going to do this at a particular point in time in the orange depth first search. What was the procedure previously? As soon as I was finding a non-A reachable state, I was checking whether it lies on a cycle. This as soon went wrong. So I'm going to adapt this ordering. I first complete the orange depth first search starting from the non-A state, and only then I'm initiating the second one. So in terms of a depth first search, this means we are fully expanded. What's the principle of fully expanded? If I do a depth first search, right, then suppose I start here, I do some search, and I reach this state for the first time. This is part of my orange thing. Yeah. And suppose this was my state S, satisfying not A. Yeah. Good. Now I reach S for the first time. If I continue my orange depth first search, so I'm just continuing here. Maybe from here there are other states reachable. Maybe from here is another reachable. And at some point, yeah, maybe in this orange depth first search, I come back in this state. Because I do something like, if I'm finishing here, I do backtrack, 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 and I get here. Yeah? At that point, I call it fully expanded. I have considered all its successors completely, and then I go back. So fully expanded means after doing the backtracking, so to speak, I will be back in that state. What is now the trick? Before we were starting the purple depth first search, as soon as we're reaching this, we have seen a counterexample. This is not the right procedure. What we're going to see, the right procedure will be, you find this state, just continue your search, the orange search. As soon as this orange search has done, has completed, at some point you do backtracking, and once you hit this state, then you initiate the purple depth first search. Yeah? And that's the key point. Good. I have some examples to show you this, how this works. So this is the important point in the algorithm. You invoke the nested depth first search only if in the outermost depth first search, the orange one, the state is what we call fully expanded. Good. Okay, so let's suppose that we have this example. This is my transition system. I have blue and yellow states, and I want to check eventually forever not blue. Good. You see immediately this holds because there is no loop that contains a blue state. Good. So I do my depth first search. I start with the blue state. Blue is fine. I start with this one. I start with that one, I continue my depth first search, I continue my depth first search there, and now I'm back in my blue state. So now I initiate my purple depth first search. So again. In the procedure before, what are the bad guys? The bad guys are the blue states. Yeah. The blue state, now, according to my procedure before, I will immediately check whether this is on a cycle or not. No, this is not the right procedure because we have seen this goes wrong. So please continue your depth first search. Continue. My depth first search says go left. Okay, so I go left. Go left. This is blue, same principle as before. It's a bad guy, but we're only checking the cycles once we are completely done with all the states reachable from the blue thing. This is reachable. That is reachable. Now we have completed the orange depth first search, the outermost depth first search, starting from this state. Now we check whether it's on a cycle or not. And checking this on the cycle is exactly this. In my slides, this corresponds to this brown cycle check. So these brown cycles mean now I'm going to check in the innermost, here the purple depth first search, if it is on a cycle or not. Of course it's not on a cycle, but now I know I never have to touch those three states again in this innermost depth first search. This is now my dashed purple area. This is those three states. This innermost depth first search now is completed. Conclusion, this state does not lie on a cycle. Let's continue. Continue means backtracking. We go back here. Yeah? We backtrack the outermost depth first search. Is there something reachable from here? Yes, there is, namely this guy. This is yellow. Yellow doesn't harm, so backtrack further. Backtrack further means go back here, check whether something is reachable from there. Yes, there's something new reachable, namely this one and that one. They're both yellow. They don't harm. Now you do backtracking, so backtrack, backtrack. I have completed my DFS, my outermost DFS from the initial blue state. So the orange DFS has been completed now. Now I'm going to check, does this guy lie on the cycle? The paradigm of the algorithm says you don't have to look in those three states, you only have to look at the remaining states. And now what you do is you look at the remaining states. Yeah? Notice that it is important to know that you not have to touch those because, of course, this is reachable from this initial state. But we now know, as soon as you reach this one, I've seen this before, it's marked as a special state, namely I have seen it before in the innermost depth first search, never touch it again. So I don't have to touch it again, and I only have to touch those other 5. Good. So in terms of pseudocode, this looks as follows. We have the set states of U. U is the set of states that we visit in the outermost depth first search. V is the innermost one. Good. What do we know? We start from any initial state, a depth first search. Why? Yeah, remember this case, I have this initial state, I have that initial state. I have to check for every initial state, is there a reachable non-A state that lies on a cycle? So that's what I do here. So this was the set of states visited in the outermost. Now I do the depth first search. I check, did I already visit this state in the current depth first search? If this is not the case, then insert it because you are just considering it. You consider all its possible direct successors and invoke recursively depth first search for those successors. Then there is this special case. If S is a non-A state, then you check the cycle. So notice that this is important. I insert S. I'm not going to check whether S is a bad guy or a good guy. I'm only continuing the depth first search. Continuing the depth first search means I'm going to consider all its direct successors and continue the outermost depth first search. Now I have completed the outermost depth first search starting from S. So I come back, backtracking in state S. Now I'm going to check, is this a bad guy or is this a good guy? If it's a bad guy, I invoke the cycle check, and otherwise I don't. Yeah. Good. So the second set I need is V, because V corresponds to this dashed purple area on my blackboard. This is the set of states that I have visited already in the innermost depth first search, so in the cycle check. Initially, of course, this is the empty set because I did not initially invoke any cycle check yet. Good. Okay, if the cycle check S, then we return no. As soon as we have found one cycle, we are done, and that's what this means, right? So I don't have to continue once I have found a non-A state that lies on a cycle, because that means that I violate this property. If I have checked all states and none of them has reached this no, then I can return yes, because I have not found any reachable non-A state that lies on a cycle. That's the conclusion. So then the conclusion is T satisfies eventually forever A. Good. Example. Same example as before, but now with the changed order. This was the example where the previous order went to the wrong conclusion. Now are we going to repeat this example slowly and see what happens. So again, 4 states. The 2 blue states are the bad guys. The other ones are the good states. Okay, I start my outermost depth first search, S0, the orange depth first search. Good. I just continue. Remember, I'm not going to check bad or good. I'm only continuing the outermost depth first search. So I'm going to outermost depth first search to S1. S1 is bad, but don't pay any attention. We just continue to S3. We go to S2. And at some point we have found now all reachable states starting from S0. Now we do backtracking, so to speak. What does that mean? Actually, now I have found S2. I have also found all reachable states from S2. So S2 is fully expanded. Yeah, go back to this picture here. All states have already been determined which are reachable. So S2 is fully expanded. S2 is a bad guy. So check whether S2 lies on a cycle. We check whether it's on a cycle. And of course it's on a cycle, because now the innermost, my purple depth first search, will start from here, then move to there, go back, and then it has found this backwards edge, which means I have found a cycle. Yeah. So before, we were, as soon as we were hitting S1, checking whether it's on a cycle, that went wrong. No, we are postponing looking for cycles once you have explored the whole outermost depth first search starting from those states. Good. And this returns the correct answer, no. Because we have found a cycle. Remember, maybe I go back quickly to this code. If you find a cycle, then return no. Yeah, and that's exactly what we need. Good. Are there any questions on this example? Is the principle clear? Yeah? Good, wonderful. Good. So you can also equip this with counterexample generation. Remember, because it's important that if I get no, no means we have found this cycle, I also would like to get a counterexample. How do I get a counterexample? Now the intuition, the details are on the slide, but the intuition is pretty simple. The intuition is that, okay, at some point I have a stack in my depth first search. I can keep track of all the states I have already started my depth first search from. So this, my stack could be something of the form, here is S0, here is S1 and S2, etc. So at some point I have a stack where S is on the top of the stack, the predecessor, I don't know, Sn is there, then here there is S2, here is S1, and here is S0. Yeah? Once this is on the top of the stack and it's bad, I initiate my purple. So this is the situation of the orange one. So this is the stack of the outermost depth first search. Now I do a cycle check. So now I start to check whether this state lies on a cycle. That again gives rise to a stack, namely a purple stack. I start with some S, and maybe I have found other states like S prime 1, S2 prime, etc. And at some point I have found a cycle, so here I found S again. How do I now get a counterexample? I take the two stacks together, concatenate them, and I have found my counterexample, because this gives a path, if I read it upside down, yeah, this gives a path starting from some initial state to the bed state, because this one violates A, and this is exactly the cycle on which it lies. Yeah, so my counterexample is, how can I reach the cycle from the initial state? And this tells you how I can reach from S as itself. That's the whole intuition. Good, so we get this initial path fragment. We formulate this with two stacks. So this is how it works. We have this set of states visited in the outermost depth first search. We now keep track of the stack. The stack is here pi, and initially this stack is empty. Then I do the same for the purple. So the innermost depth first search, initially I have not visited any state. So V equals the empty set, and initially that stack is empty. Good. As long as there are initial states that I have not visited before, I choose some initial state and insert it into U. This is still part of the orange outermost depth first search. I push it on the stack. That is the difference with the algorithm I had before. I had no stack. So here I push S0 on the stack. That's exactly this S0, which is when I found S on the bottom of the stack. Good. Now, as long as the stack is non-empty, take the top of the stack. If this state has successors that I did not yet consider in the outermost depth first search, then consider them, which means pick one of those states, insert it into S, into U, and push it on the stack. Else, if all successors of S have been completed, you can pop it from the stack because you have finished your orange, the outermost depth first search starting from that state. And now you're going to check. That means I have completely completed my orange outermost depth first search starting from A. Now you check if S is a bad guy, check whether it's on a cycle, and return no. Good. What is now the counterexample? You take the stack pi, which is this stack in this depth first search. Within the body of cycle check, we're going to use this stack psi, and what you do is you go basically concatenate them and reverse the order. You know, reverse the order because, as you see, I have to read the stack from bottom to top, not from top to bottom. That's what the reverse does. Good. This is the cycle check. I think it's relatively, I hope, if you understood the first one, the first DFS, then this is also not so difficult. So now this is the innermost depth first search, so the cycle check. You start pushing S on the stack and insert it into the dashed purple area. This is the state I have seen before in the innermost depth first search. As long as this stack is non-empty, take the top element. If it has direct successor that you did not visit so far, yeah, then return true. So you push it and you return true. If otherwise, you check whether there are any successors that you have not considered yet in the innermost depth first search. Then what you do, you choose such a state and you continue the depth first search from there by pushing it on the stack. Otherwise, you pop it, and if you're completely done, which means if you don't find any of those states, you don't have to do anything, and in the end, you return false if you did not found any cycle so far. Good. So here you see what happens if this S belongs to post S prime. That means this is the situation of the stack, right? You started from S. That's what you pushed on the stack. At some point, you take the top of the stack, so that's S prime. And apparently, you find that S is a direct successor of S prime. So this state here is a direct successor of S prime. That means you have found this backwards edge, and now you have found the cycle. So that's why you get this return true. Yeah? That's what it does in terms of a picture. Good, and that means you push. Good, I skipped this. The most important point is the proof of the correctness of this algorithm. So that's what I call the soundness of this nested depth first search. So remember, in the outermost depth first search, I visit all the reachable states. in the innermost depth first search, I check for cycles. And you only check a cycle if S is violating A, and you do this when the outermost depth first search, the first one, is finished starting from S. That's the key point. That was the point at which we're invoking the nested depth first search. Good. And we have those global data structures V. V was the dashed area, Xi is the stack of the innermost depth first search. Good. So termination is not so difficult to prove, but the correctness or the partial correctness is the key point. Good. So what do we need to prove? The correctness is given as follows. T satisfies eventually forever A if and only if the nested depth first search returns yes. That's the correctness criterion. Good. So this is what we need to prove. T violates eventually forever A if and only if the nested depth first search returns no. Proof of this direction. So assume the nested depth first search returns no. No means it has found a cycle. Good. So if the nested depth first search returns no, then there is a reachable state violating A which lies on a cycle. Yeah, but then we're done. So that is hopefully clear. I mean, that was exactly the picture here. If indeed there is a non-A state that lies on a cycle and I have found it, I can conclude the transition system violates eventually forever A. Good. That's the easy part. Good. Now there is also a part, because now I can reach from some initial state, state S, and S lies on a cycle, and this is the cycle on which S lies. Good. The hard part is this part. T violates eventually forever A, and now we have to prove that the nested DFS returns no. Good. So the key lemma is the following. The key lemma says, if you invoke the cycle check, remember the key point is when do we invoke the cycle check? Yeah, so it's not so surprising that in the correctness proof there is some lemma that says exactly if you invoke it on the right time, you get the right answer, basically. So if you invoke the cycle check, then there is no cycle in my original transition system that contains S such that those cycles belong to the dashed area. So go back to this state. The statement is saying, okay, this is the situation. We have found this state, not on a cycle. That state, not on a cycle. This one, maybe, we're not here. So we are going to invoke the cycle check for this state. Let's call this state S. Then the lemma says the following. The algorithm guarantees that there is no cycle containing one state in this purple dashed area to which S belongs. Yeah? So in terms of a picture, this is not possible. Yeah? These cycles cannot exist. So this gives you exactly the reason why you don't have to look into those dashed areas again. Yeah? That's the point. Good. Hence, if S belongs to a cycle, then cycle check S will find a backwards edge from some state to S, but this state does not belong to V. Good. I think my time is over. Otherwise, I would have some more explanation why this is the case. There are some further improvements. I want to skip them here for this moment. There are some further improvements. So this nested depth first search by Pelet, Vardi, Wolper, Yannakakis. The first tool that implemented this was Spin. And now I see that I miss one of the authors. That's Holtzman. Because he took this algorithm and implemented it into Spin. And that showed an enormous performance improvement with respect to the previous algorithms they had in model checking using this SCC decomposition. Okay, thanks for today. Next lecture, Tuesday, next week.